Same stuff as before, just got a little addition to the family here. Took out the lines, put in a scatter of points. We're going to talk about estimation. So, you might want to look back to your notes, or you might even want to key up the old video when I introduced the idea of estimates, estimation, and estimators. Estimation being the process of using sample data to say something about population data, in particular parameters. Now before, when we used this concept, we had x bar being the sample mean and mu x being the population mean. And so we identified this as a sample parameter, this is a population parameter, and the term estimator is about the formula that you use to estimate this using sample data. And it's real simple here. It's the sum of the xi divided by n, add them all up and divide by the total. As it turns out, and I may be able to squeeze in, we're getting close to time for school, but I may be able to squeeze in an optional video on estimation, and I may not. If I don't, for anyone interested, I'll do a private show. So, but this is a particular kind of estimator. It's called the least squares estimator. In the video on estimation, sample mean to population mean, I explained properties of estimators and pointed out that this one had some really good ones. The sample mean is an unbiased estimate of the population mean. It is an efficient estimator of the population mean. Look back at that stuff. If you need to latch on to that to come back here, mark your tongue. And so we're doing estimation. This time, instead of sample mean to population mean, we're doing the intercept and the slope. So this is called, saw this in the last video, I've redone it up here. Sometimes have the Greek letters alpha and beta as population parameters that relate data in the population in a straight line. We're assuming a particular kind of relationship between these two variables. We'll call this y, and this is x. We're assuming the relationship is linear, which means it follows a straight line. So I've plotted points in the space, assume it's a Cartesian plane, plotted points in the space, and refer now back to where we finished the last video. So this is going to be as x bar is to mu, a is to alpha. As x bar is to mu, estimation from sample to population, b is to beta. We care about what these things are, and we wish to estimate them using sample data. So first we have to find them. We began with only a scatter of points. When we first start with regression using R in the classroom, that's where we're going to start, is just a scatter of points, and then fit a line to the points, and a line of the form arithmetically like this one, yi equal a plus bxi plus ei. Remember now, the error is the distance between an observed value of y and where the value of y would be on the line if all you had was the formula. So given that, we're going to give a little more definition to the error. So ei in particular is equal to, here comes a boat. I'm going to put a hat on y here to denote the point on the line defined simply by y equal a plus bx I, and then the observed value of y no matter where it is. And as it turns out, then I can sum across these. Sum across every one of them. yi minus hat plus 1. sum across them, square them. I'm doing estimation here, nothing really hard. Sum across them, square them. I won't do this because I won't require you to produce it. But what I would do next, if everybody in the room knew just a little bit of calculus, even just like a smidgen, and we could require it, what I would do next is I would replace y hat I with what it really is, a plus bx. Then I would have a little bit more elaborate sum of squares. Then I would, horror of horrors, differentiate the sum of the squares, set the derivatives equal to 0, and solve for the parameters a and b. When I did that, I would be doing, and you do need to know this, I would be finding the ordinary least squares estimates of a and b. Ordinary least squares. This technique is owed to the German statistician and genius Carl Friedrich Gauss. I want you to know that too. It's one of the foundations of statistics. And when I talked about the central limit theorem, I said, well, there's a big one. Least squares as an estimation strategy is also a big and foundational idea also. Ordinary least squares in this case, because there are all kinds of other options. If you ever take a more sophisticated course down the road in something like this, you'll see this was your foundation with a straight line. So I solved for a and b algebraically after I've differentiated the sum of these squares and set the derivatives equal to 0. And there's a closed form solution. There's one solution to this problem in ordinary least squares, and it finds the line. It finds the a and the b. If you want to put a hat on these guys, you can. Make up your own notation. Just remember that they are they're estimated from sample data, and the intended estimation target is the two population parameters that will relate these two variables, x and y. And so then I've got a finished product here. So I've got real values for a and for b. I've set this thing so that the intercept, the estimated a, is going to be 2, right? And so roundabout, the estimated slope of that line is going to be roundabout 1. Visually, that's the way it looks to me. Visually has nothing to do with ordinary least squares. Ordinary least squares finds, write this down, the line that bisects these points by coming as close as possible to every point at the same time. This is when it's summing across these squared distances. Then differentiating, don't worry if you don't know how to do that, it just means minimizing the sum of the distances, and finding at the end of the day an estimate for a and b that define a line that comes as close to as many points as possible at the same time. It's a unique line, and its two parameters, the only two that define it, the intercept and the slope, they have good properties, estimation properties. In particular, given a set of assumptions, sometimes these assumptions hold, sometimes they don't, but ordinary least squares is really robust to assumption violation. So, but given a set of assumptions, OLS estimates are unbiased and efficient. As estimators of their corresponding population parameters. The next video is a little bit about what those assumptions are, and a lot about the idea of unbiasedness and efficiency in the context of inference. And once again, we're going to build confidence intervals. And once again, we're going to say something about statistical significance associated with sample statistics that aim to estimate population parameters. That will be in video 3.